Hi students, this is lesson 7.4 and we will be learning about geometric series. And we're going to have two new formulas to be able to add to our collection here of tools. So our learning goals are the same. We'll be evaluating a series and we obviously have to determine if it's arithmetic, geometric, or neither. And we always need to do that in order to see what tools we are able to use. So just as a review of what we've already learned, on page 3 you have a formula page. So I want you to make sure that you're adding as we go. For sequences, remember sequences are where we're separating things with commas. Those terms are separated with commas. We found the nth term for the arithmetic and for the geometric. So we're able to get that formula. Now series is where we're actually going to add those terms together. And so we've already talked about arithmetic with the Oh My Gosh worksheet, where we have the total number of terms, that's my n, the first term plus the last term, and that, after we get that sum, we multiply by n, and then of course we cut it in half by dividing by 2. The last two formulas are the sum of a geometric series. And what we're going to learn about today is finite, or with an ending, or infinite series, which means the terms will go towards infinity. They'll never end. Okay, so finding these geometric series and making sure that we know that they are geometric, we know that we have to have an R, or a common multiplier. So to find R, we can always take, let's say, the nth term and divide by the term right before it. So all this means, this is A1, A2, A3, and A4. We could say R is the same as the second term divided by the first term, which would be 2.5 divided by -5, which is -1/2. Now we would have to go ahead and verify that this worked, and from there we could just multiply each term by -1/2. But some of these will be a little messy, so make sure that you know and you have written down to find R, we're really going to take that second term, divide by the first, the third term, divide by the second, so on and so forth, and it should all be that same R value. Once we identify that we have a geometric series, we're going to be able to use our geometric tools. So that's really important that we're able to do that and understand that. So these are all being multiplied by 3. And again, we can just say, okay, the R value is 3. So we've done that already, but really important, that's how we're verifying that we do indeed have a geometric series. Now, this is on page, I think it's page 5. I might be wrong on that, but this is in your packet. Packet's not too big. You should be able to flip through and find that. And this is going to be how we're going to get our formula for the sum of, remember, this is finite, or with an ending, geometric series. So with this page, we're going to go ahead and fill in either the reasons or the actual steps on the left, the process. And this first one is filled out entirely for us. So it's saying we want the sum of the first n terms. So you can tell we're starting at term 1 and we're ending at term n. This should look very familiar. That is actually the formula for the nth term. We have the first term times the common ratio raised up to the term number, take away 1. So this is the formula, and we could go ahead and plug in values 1, 2, 3, 4, 5, 6, 7 until we get to n, whatever n may be. So this is just saying, explaining the summation notation. Now the next one is talking about expanding the right side. Write it in terms of a sub 1, r, and n. So what we're going to do is we're going to go ahead and say that the sum of the first n terms, well, let's think about this. Let's plug in 1. The first term would be a sub 1 times r to the 1 take away 1 plus a sub 1, we're going to plug in 2 now, r to the power of 2 take away 1 plus, I'm going to do some dots here. Maybe I'll do one more. Hold on. Maybe I'll just do one more. So a sub 1 r to the 3 minus 1. And then obviously there's terms in between. We don't know how many. And then the last term is going to be when I plug in n. So a sub 1 times r to the n minus 1. I'm going to clean this up a little bit because it's going to help us in our next step here. So 1 take away 1 is going to be 0, and anything to the 0 is 1. So we just have a sub 1 here, plus a sub 1 times r to the first power, plus a sub 1 times r squared, plus a sub 1 times r to the n minus 1. And that is what you're going to see down here on the next line. So we are going to say what happened here. Well, let's look at the difference. The s sub n was here on the left. It's still here on the left, but now look what's with it, this r, and we see it's over here as well. So what do? We multiply both sides by r. Okay, the next line is telling us, hey, distribute that r on the right. Okay, so we'll just go ahead and multiply that into all these values. So we get r, sum of the first n terms, that's on the left, a sub 1r plus a sub 1r squared plus a sub 1r cubed. And of course this keeps going, and then a sub 1 for our last one, r to the n. Okay, and again, this is just our algebra in terms of using these exponent properties is what we're doing. The next thing is showing us, look at, we have this, which is from step 2, and we're going to subtract what we just did in step 4. And you're going to see, hopefully, what this is going to do for us. But let's say we subtract step 4 equation from step 2 equation. All right, now once we do that, look what happens here. So s sub n, take away r s sub n, we can't combine those, so that just stays as is. Look what happens when I subtract. All this middle stuff is going to go away. And so we're only left with s sub n minus r s sub n equals a sub 1 minus a sub 1 r to the n. And please mark down questions here. So anything that you're like, wait, what happened here? Make sure you're marking those down. We can go over that in class together. The directions here say, hey, factor out the greatest common factor from each side. Okay, well, what's the same in this? The left side is s sub n. And what's left? 1 minus r. Okay, on the right side, the common factor is a sub 1. What's left? 1 minus r to the n power. How did they get s sub n alone? Well, they must have divided both sides by the quantity 1 minus r. So that's our direction here, as we divide both sides by 1 minus r. We need to remember that r cannot be 1 and r cannot be 0. If we go ahead and plug in those values, we're going to see we're going to have some issues, and we're going to get into that more later. But those are the restrictions for the value of r. Okay, so from here, we have our formula. The sum of the first n terms of a geometric finite series. We take the first term, we multiply by 1 minus the ratio, where the ratio is actually raised to the nth power, and then divide by 1 minus the ratio. So now we have this last one, this finite one to fill in. So on page 3, make sure that you have that recorded carefully. And the last thing we'll do is the infinite. So this was page 16, sorry, the formula page. So explain what each of the components in the formula represents. So for this, when we're talking about this, this is the sum of n terms. This is the first term's value. And R is the common ratio. And what's the purpose of the formula? Why is it useful? So for something like this, we don't want to list out 50 terms and add them all together. So this allows us to be more efficient in actually using this formula. If it's only 3 terms, sure, list them out, whatever. But if it's 50 terms, there's no way we're going to want to take the time to calculate all 50 terms and then add them all together. So this is something that is going to help us with efficiency. Okay, now we're going to look at infinite. Take a look here. This tells me those terms are going to keep going and going and going. And we want to know what is the sum, which seems a little ridiculous because if I keep adding more and more and more, you would think we wouldn't get a sum. Something like this here, for an infinite amount of terms, there is no sum. It's going to go to infinity because these values keep getting larger and larger. And R is 3. Now in this one up here, these are the same ones we looked at previously. R is a negative 1/2. These values are going to continue to be smaller and smaller and smaller. So we're going to converge to an actual sum. Even though these terms go to infinity, we're still going to converge to a value. So let's take a look at how this works. So first of all, we already know the formula for the finite geometric. We just looked at that. That's the one that we just did. Okay. And now what we're going to do is we're going to think about, hey, as the number of terms go to infinity, what might happen? So let's write this down. The limit as the number of terms go to infinity. And we're going to use this same formula, but we're going to see what happens to the formula. What happens to this sum? Okay, as n goes to infinity, that means we have this R value to infinity. If R, let's do the absolute value of R, is less than 1, okay, and if we want to say here, and R is not equal, let's see here, to 0, okay. So the ratio has to be something other than 0, because if we're multiplying by 0, that doesn't make sense to get from term to term. If the R value, the absolute value, is less than 1, we're thinking of something like a half or a negative 1/2, and we plug in a huge number up here. That R to the n is going to approach 0. And go ahead, type in, 0.5 to 100. What do you get? In parentheses, negative 0.5 to 100. What do you get? So that is going to become negligible. Okay, so since that's the case, it's going to be a sub 1 times 1 minus 0. And this, again, this is as the n gets huge over 1 minus r, which is just a sub 1 over 1 minus r. And that's actually your formula. This is the sum of infinite terms for a geometric series. If the absolute value of R still is not going to be 0. If this is greater than 1, there is no sum. You may not use this formula as the terms increase, the value of the sum will keep increasing. Okay, it's not going to converge to a certain value, and it could be a negative outcome as well. But we're not going to bounce to one particular value. It's just going to keep increasing or keep decreasing as the terms go to infinity. Okay, last definition here. This is only for geometric. If we have an infinite geometric series, we can take the sum, but again, we have to be very careful. R cannot be 0, and the absolute value of R must be less than 1. That is critical in order to be able to do this, to use this formula. All right, we're going to try a couple examples with our formulas. We're just going to do 2 examples, then we'll practice more in class. So this first one, before we get started, we need to say, okay, so here we have 3 terms. Is this geometric? Otherwise, we can't use that formula. So to get from 8 to -4, I would multiply by a -1/2. Does that happen again? Times -1/2. It does. So R is -1/2. Okay, this is geometric. So on that graphic organizer, now we get to use all the geometric tools. So to get the sum of the first 11 terms, we need the value of the first term times 1 minus the ratio, must be in parentheses, raised up to, in this case, the 11th power. And that's all divided by 1 minus that common ratio. When we evaluate this, we should get approximately 5.335. Find out if it's geometric. Use the appropriate formula. For example 2, we can see this is geometric. Look at our repeated multiplier. We multiply by 1/3. And now it's saying, hey, go all the way up to infinity terms. Well, we're not listing out infinity terms, okay? So we need to say, hey, is there a formula? And yes, we just learned what that formula was. So we're going to go ahead and use it. We're going to say the sum of infinite terms is the first term. Well, let's see. What is the first term? 27 times 1/3 to the first, which is 9. So go ahead, put 9 as your first term value over 1 minus the ratio. Now, what's the ratio? It is 1/3. That's our common multiplier. So 1 minus 1/3. And this is going to equal 13.5. Identify it's geometric. I know my R, I know my first term, and I can use the appropriate formula. Okay, we're definitely going to practice more. Please write down any questions you have, and make sure you have that graphic organizer filled out with all your possible tools for the series.